Good afternoon, everyone. This is Ling from Florida State University. It's a pleasure to be here to present to you our latest work, VibLive, a continuous liveness detection system for secure voice user interface in the IoT environment. To understand the motivation of our work, let's first take a glance at what voice user interfaces can do now. Indeed, when we think about it, recently, voice user interfaces on mobile devices, smart speakers, tablets, enable access to all kinds of IoT devices by voices. For example, in the smart home environment, the voice user interfaces have greatly facilitated almost every aspect of our lives, from security control, appliance control, to even personal business control. In these cases, the VUI devices have access to our security systems, appliances, and even very personal information. Similarly, in a smart office environment, the voice user interfaces are deployed to improve the security, efficiency, collaboration of the whole workplace. For example, they could support voice authentication-based access control to some special locations devices. They could also provide easy environment control over temperature and light, and they could be used for centralized administration of the teamwork. Besides, voice user interfaces are well adopted by smart vehicles, where they enable direct communications between the driver and the car. The driver could ask the in-car voice assistant for navigation, making phone calls, playing music, or she could even require hands-free driving services while they control the car with only voice commands. Though convenient, such unlimited trust on the voice user interfaces could expose ourselves to the attackers. Indeed, voice user interfaces rely on the voice authentication technology to authenticate legitimate users and their commands. Unfortunately, state-of-the-art voice authentication systems are still vulnerable to replay attacks, where a malicious party spoofs the voice authentication system with pre-recorded, concatenated, or even synthesized voice samples of the genuine user. Conducting replay attacks requires no expertise or specialized devices. Nevertheless, they are highly effective. Successful attacks on VUI may cause severe consequences, such as credential breaching, privacy leakage, security system failure, or even malicious vehicle misleading. To resist such attacks, we propose VibLive, a liveness detection system for protecting voice user interface-based devices. Comparing with previous research, VibLive has three primary features: continuity, transparency, and applicability. It secures the whole communication session continuously and transparently with only normal microphones and speakers on the voice user interface devices. Moreover, VibLive is capable of liveness detection from both short-range and long-range IoT applications. We design our system and attack models based on the state-of-the-art VUI-capable device workflow, which mainly composes of two phases: the activation phase and the speech recognition phase. Some devices will simply be activated with the right wake words and execute any commands after it's been activated, whereas other devices support a higher level of security by adopting voice authentication for activation phase and using speaker-dependent speech recognition to block commands from illegal users. Unfortunately, these protection measures are not enough, and replay attacks could happen at both phases in either case. To protect the VUI continuously, VibLive keeps conducting liveness detection during the whole communication session. We built VibLive on the underlying principle that, when human articulating, we generate both air-conducted voices and bone-conducted vibrations, and these two signals are different. By contrast, for a loudspeaker, it vibrates and plays according to the input signal. It asks, the rigid body vibrations and the replayed voices are always the same. Especially, as soon as hearing the wake words, the device's speaker emits an ultrasound probe signal, which then will be reflected by the vibrating human skull or the loudspeaker body. These reflections, as well as the air-conducted voices, can be recorded by the device microphone. Now let's see why air-conducted voices and bone-conducted vibrations are different. The answer is that they go through different medium and modulations. despite of the same sound source of vocal folds. To form air-conducted voices, the vocal folds vibrations first pass through the vocal tract via air conduction, and then be modulated by articulators like lips and tongues. And at last, the modulated formants are emitted to the environment by human mouth and nose. The air-conducted voices could be recorded by a normal microphone. Whereas, to generate bone-conducted vibrations, the primary vocal folds vibrations transmit and be modulated by the soft tissues, skins, skull bones. The bone-conducted vibrations are barely emitted to the environment, and they could only be picked up by contact microphones. Here is an example showing the differences between the air-conducted voices and bone-conducted vibrations for some phonemes. We could observe that, for these phonemes, the bone-conducted vibrations and the air-conducted voices can be different in overall power distribution, formants power and number, power distribution of specific frequency bands. Therefore, our system catches this difference to detect a live user. This is an overview of our system realizing liveness detection in a real user case. In an IoT environment, as soon as the VUI-capable device is activated with the wake words, the built-in speaker of the device begins to send an ultrasound probe signal. This signal transmits by air and then be reflected by the human or the replaced speaker. Meanwhile, the built-in microphone keeps listening and collecting the reflections of the probe signal as well as the voices. Then we separate the reflections from the received signal and recover bone-conducted vibrations. Last, we extract linear prediction spectrum features from both voices and vibrations for comparison and make liveness detection. We realize VibLive with 3 main modules. Let's go through some critical steps in details. First, we have mentioned that the probe signals will be reflected by the speaker. Indeed, in a short period of time, when the human head vibrates at a specific frequency f0, we could calculate the displacements with the first formula. Meanwhile, the head displacement causes the probe signal propagation distance changes. According to the relationship between the propagation distance and the power of the sound signal, we could deduce that the probe signal power change is inversely proportional to its propagation distance. Thus, we could extract the head vibration signal by examining the power changes of the reflected signal. Specifically, after separating the voice signal and the reflected probe signal of M samples, we calculate the sound pressure level of every endpoint. Then we combine the sound pressure levels as the recovered vibrations. Next, we compare the recovered vibrations with the recorded voices. According to the differences between the bone-conducted vibrations and the air-conducted voices, we choose the linear prediction spectrum for feature extraction. A higher order of LP spectrum could catch more details of the modulation of the signal. Empirically, we choose the 15th order LP spectrum. Instead of matching the whole spectrum, we extract the peaks of these spectrums for similarity comparison. Before comparison, we match the peak numbers of the spectrums. Moreover, to tolerate the frequency shifts of the recovered vibrations, we match the peaks that are close enough in the frequency axis. Whereas, if we cannot find the matching peaks, we pad 0 at that frequency point. The figures show an example of before and after peak matching. To verify our system, we conduct our experiments with 3 types of phones. One Google Home microphone-grade external microphone. We have conducted both short-range and long-range experiments with 25 participants. We have conducted replay attacks with 3 types of loudspeakers. Furthermore, we have designed an experiment with 3 types of target attacks in case the attacker have learned the methodology of our system. The overall performance shows that our system achieves over 97% accuracy with around 1% false positive rate. And for the overall performance under different ranges, we observe that our system is valid in both short-range and long-range applications. Other than replay attacks, we experiment on targeted attacks. For the occlusion attacks, we occlude the loudspeaker with different objects. We do notice that when the objects get thicker, the accuracy of our system does decrease. Nevertheless, the accuracy is still above 93% with a 12 mm thick hardcover book. Besides, the attacker normally has no control over the location of the speaker, and the user would barely cover the loudspeaker. For the low sound pressure level attacks, we use low sound pressure level to reduce the vibrations of the loudspeaker. We do notice that when the SPL is under 50 dB, the accuracy drops to around 90%. However, when it is below 50, may be too quiet for the VUI microphone to pick up as well. And for the angle attacks, we try to reduce the size of the reflector, thus to disturb the vibration sensing. The results show that our system performance are barely affected with such attacks. These are the conclusions of our work. We designed VibLive for secure VUI in IoT environment in both short-range and long-range applications. We developed an approach to allow the VUI-capable devices to sense the bone-conducted vibrations without extra hardware. VibLive supports text-independent liveness detection, thus could protect the whole communication session. Experimental results show that VibLive is effective in various setups. That's all. Thank you. You're welcome to ask any questions.